Hello students, my name is Shashank Shekhar. So today we will talk about lanthanoids and actinoids. So we have done the transition metal elements. Now we'll talk about the inner transition metal elements. So if you remember, then two separate rows were attributed to this lanthanides and actinoids, and they are present at the bottom of the periodic table, right? So there are 14 elements in lanthanoids and both in lanthanoids and actinoids, and the 14 elements are after lanthanum and actinium. So if you just look at the periodic table, you will see that after means before lanthanum and before actinium, the lanthanoid and actinoids are there, but they are placed in the bottom of the periodic table. Clear? Now, lanthanum is usually included in any discussion of the lanthanoids. So if you're just talking about lanthanoid, the lanthanum are also included in that say in that discussion. So, and similarly, the actinium is also included in the actinoid discussion. So they are similar to, means lanthanum also belongs to the lanthanoid section, and actinium belongs to the actinoid sections. Now, lanthanoid resembles each other more than do typical transition elements. What is the meaning of this? So, if you see the properties of lanthanoid, then they are identical, right, to each other. Unlike our transition element, in which the chemical reactivity varies, this lanthanoid have a similar property. Means they are almost identical in their reactivity. Now they have one stable oxidation state. Okay, they have one stable oxidation state. Means for all the lanthanoid, we will see that there is a common stable oxidation state, and their chemistry show effects of small changes in size and nuclear charge. So if you just move to left to right in the lanthanoid section, then you will see that their atomic size is not varying that much, and nor their nuclear charge. Now since this ratio is same, now due to that reason they are having a kind of same reactivity, whereas actinoids have a complicated property, or you can say a complicated chemistry as compared to lanthanoid, because they have a wider range of oxidation state. Also, the radioactivity of the actinoids creates a problem studying them because their mass changes continuously. So if something is changing its mass continuously, then it is difficult to study that compound. Now the term lanthanoid was adopted originating from the first element of the series, that is lanthanum. We know this. Now, lanthanoid has similarities in the electronic configuration which explain most of the physical similarities also. Means the electronic configuration is same, and due to that reason, they have a resemblance in the physical properties also. And these elements are different from the main group element in fact that they have electrons in their orbital. Now, after lanthanum, the energy of 4f subshell falls below that of 5d subshell. This means that the electrons start to fill 4f subshell before the 5d subshell. Okay, so before 5d we fill the 4f. So it is very clear. If you just calculate the n plus l value of both of this, then n plus l value of 4f is how much? So for s, the value of l is s, p, d, f, means 0, 1, 2, 3. 3 is the value of what? L. So 4 plus 3, 7. And for 5d, it is also 5 plus 2, 7. But since 4f has a smaller value of principal quantum number, so it will have a lower energy. So according to above principle, we will fill the 4f orbital first. Clear? Now the name, the symbol, the electronic configuration of different lanthanoids are given here. Okay, so we'll see that chart. So the names, the symbol, electronic configuration of atomic and some ionic states, and atomic and ionic radii of lanthanoid and actinoids, right? So this is about electronic configuration. Let us talk about electronic configuration. Now +3 is the common oxidation state or stable oxidation state for lanthanoids. Okay. Now, if you see here, this is the table regarding the electronic configuration. So, all have a full filled s orbital. So, this first thing is common in all of this. So in lanthanum, cerium, okay, and in all of these lanthanoids, we can see that they have a fulfilled s orbital. The 6s2 is common in all of this. But there is a what? There is a exception. Where is the exception? First exception is here in case of 5f1, 4f1, 5d1 for cerium. So this is the first exception. Okay. Now here it is very important thing. So if you just remove one, say 2 electrons from lanthanum, then instead of getting any other electronic configuration, we will get it as 4f2. Okay, 4f2 means the electron in the d orbital will come back to f. Clear? So as we remove cs, the 2 electron of 6s, you will see that the one of the electron of 5d, which is singly occupied, will come to 4f, and we will see 4f2 configuration. Similarly, for ln3 plus, the configuration is 4f1, but for ln4 plus, all electrons are removed, so therefore it is 4f0. Now talking about the radii, you can see that their radii is not varying that much. Okay, you can see that we can move from 173 to 187, and we are covering all the elements, right? Here also the ionic radii is also not having any significant change, so it is decreasing. Of course it will decrease because effective nuclear charge is increasing by small amount. So 106, 103, 101, 99, 98, 96, 95, 94, 92, 91, 89, 88, 87, 86. So it is decreasing. Okay, although the decrease is not that significant, but they are decreasing. Now in the plus 3 oxidation state, the atomic radii of plus 3 oxidation state is also what, almost similar. So they have a similar chemical properties. Here also the normal lanthanoid in its zero oxidation state have a what, they have a very small change in the atomic radii. So if I just conclude all of this, so the important point is, first of all, if you look at the electronic configuration, so cerium and gadolinium, okay, they have exception. So the gadolinium is having exception because it is having half filled f orbital if we take it as 4f7 and 5d1. So what can be inferred from here? So instead of filling the 4f and 5, sorry, instead of filling the 4f first, we are going to 5d. It means that the energy gap between 4f1 and 5d1 is very small. So it can easily go to 5d. But as soon as we remove 2 electrons, you can see that their energy difference changes, and the electron from 5d jumps quickly to the 4f2. Clear? So one exception, two exception. Here also in the lanthanide 2 plus, you can see there is one exception here, that it should have been 4f1 5d1, but instead it is 4f2. Clear? Okay. So this is all about the electronic configuration and atomic and ionic radii. So if I just conclude this, so these two are the exceptions in the lanthanum. In the plus 2 oxidation state, the cerium is a exception, and we are having a decrease in the we are seeing a trend of decreasing atomic radii and both the ionic radii, although the radii change is not that significant, but still it is decreasing. And due to this insignificant change in atomic radii, the effective nuclear charge almost remains same, and hence we see similar properties of the lanthanides, both in the normal state and in the plus 3 oxidation state. Clear? Okay. Now lanthanoid contraction. Now I'll talk about lanthanoid contraction. So you must have heard this term when we have studied the DNF law. We have seen that when f orbital is filled before the 5d, means the 4f orbital is filled before the 5d, and when it gets fulfilled, and after that the d electrons are fulfilled, then you will see that a greater effective nuclear charge is observed, or you can say experienced by the 5d electrons because of the poor shielding effect of the 4f orbital. Clear? Now this lanthanoid contraction also affects the atomic and ionic radii from lanthanum to lutetium. And why it is so? It is because of the imperfect shielding of the 4f electrons. Clear? So this imperfect shielding, this decreases the shielding. A decrease in shielding results in increasing nuclear charge. Okay. Now this contraction has consequences for the chemistry of third transition series. We have seen that their atomic radii remains almost change for the lanthanoid, but in the case of transition series, it decreases in a greater to extent to a greater extent as than the expected trend. Clear? Now the cumulative effect of lanthanide contraction make it difficult to separate elements like zirconium and hafnium, which have nearly identical radii. So see, this is the radii, ionic radii. So it is decreasing easily, right, in a linear fashion. So moving on to linear lanthanium 3 plus to lutetium. Okay, lutetium 3 plus. Clear? Okay. Now we have some for we have ionic radii of some 4 plus ion also tetravalent. So cerium and promethium. So only these two can be measured. So that is the reason these two are mentioned here. Similarly, for 2 plus europium and CSM has been measured, and similarly for this white terbium and TM has been measured. For that reason, we are only seeing the ionic radii of these scattered elements. Similarly for TB4 plus, it is here. So if it was possible to just calculate the ionic radii, it would have just gone like this. Clear? Okay. So a very important point here that only lanthanium 3 plus ionic radii can be measured. Okay. So for all of this elements in the lanthanoid, only 3 plus oxidation state ionic radii is measured because it is stable. Okay, because it is stable. Now let us talk about their physical appearance. So they are silvery, white, soft metal, and they tarnish rapidly in air. So why are they tarnishing? Because they must be they would be reacting with oxygen and forming the oxides, right? In the presence of moisture, they must be reacting with oxygen and forming the oxides, and due to that reason they are getting tarnished or they are getting corroded. Now their hardness increases as we increase the atomic number. So as we go on increasing the atomic number, you will see their hardness increasing, and their melting point ranges between 1000 to 1200 Kelvin, except samarium, which is 1623. Okay, so this is the exception in the melting point of samarium, which is 1623 Kelvin. Now, typical metallic character. So they have a typical metallic character. They are good conductor of heat and electricity. Density and other properties change smoothly except for europium and yttrium. Many trivalent and ions are colored both in solid state and aqueous solution. So these are some common points that are regarding some general characteristics of lanthanoid. Okay. Now, if you talk about the color, so color is attributed to the presence of f orbital. So two of like lanthanum and lutetium, so they don't show color. Now, adsorption bands are narrow, excitation within f level. So what does it mean? So they absorb a very small band in the spectrum. What is the reason behind it? Means their absorption is occurring only between what? Only for the f orbital, only for the excitation that is limited to f orbital. So here also the f orbital are getting means the degeneracy is removed and they're getting splitted, and due to that reason there is a chance of what? There's a chance of transition, and this transition is done by with the help of what? Falling light or spectrum. Now, since the energy gap between the two splitted f orbital is very less, for that reason we see a very small adsorption. Now, ions other than F0, that is lanthanum 3 plus and cerium 4 plus, all are what? Paramagnetic, F0 and F4. So if we talk about F0, we have lanthanum 3 plus and cerium 4 plus, which is F0. And if we talk about Fp plus, F4, F14, then yttrium 2 plus and lutetium 3 plus is fulfilled. Now, since both of this have no unpaired electron, okay, they have no unpaired electron, so they are all what? Dimagnetic. Now, except these four, all are what? All are paramagnetic. So this is very important that only lanthanum 3 plus, cerium 4 plus, sorry, lanthanum 3 plus, cerium 4 plus, yttrium 2 plus, and lutetium 3 plus are dimagnetic. Except these four, all are what? All are paramagnetic. Means 10 of the elements are paramagnetic. Now, talking about the ionization enthalpy, the first ionization enthalpy of lanthanoid are 600 kilojoule per mole. Okay, and the second ionization enthalpy is 1200 kilojoule per mole. If you talk about the third ionization enthalpy, they show a certain degree of stability to empty, half-filled, and completely filled d orbital. Abnormally, the low value of third oxidation state is for lanthanium, gadolinium, and lutetium. Okay, and why is it so? Why these three elements show a low value of third ionization enthalpy? Because they are either moving to a half-filled orbital state or a full-filled orbital state. Clear? Okay. So you can just infer it from here also that lutetium 3 plus F14 and lanthanum 3 plus has F0. Okay. Now if we talk about chemical behavior, then the earlier member are more reactive. Okay, means the one which are the lanthanides which are having a smaller atomic number are more reactive than the one which are having a greater atomic number. Now the initial members will act as calcium, while the later on members which are having a greater atomic number, they behave like aluminium. So talking about the reduction value, so this lanthanium 3 plus 2 lanthanium, this reduction potential lies between minus 2.2 to 2.4, except europium which has minus 2.0. So see, all of their characteristics are almost similar. Even their color are similar. They all are silvery metal, right? They all have metallic property. They all have a stable oxidation state, which is plus 3. They all are having the same reduction potential, which is minus 2.2 to minus 2.4. And what are all these similarities are attributed to? So they all are attributed to the charge is to radius ratio, which is similar for all of these elements. Clear? Now they react with hydrogen to form LNH3. Okay, this is they are going into the plus 3 oxidation state, and plus they react with carbon to form Ln3C, Ln2C, 3, and Lnc2. So these are the three oxidation states that are possible for lanthanoids. Three compound that are possible for lanthanoids, whereas for hydrogen it forms only NNH3, where lanthanium is in plus 3 oxidation state. Now here is a diagram that represents the reaction with each of this. So if you just burn lanthanium in oxygen, it is going to plus 3 oxidation state here. You can see very clearly. Also, on reacting with acids, it releases H2, which shows that they are metals. On reacting with halogens, they again from the plus 3 oxidation state, that is LNX3. Now, they react with H2O to give LNOH whole thrice plus H2. With carbon at 2773 Kelvin, it reacts to give LnC2, and when they are heated with nitrogen, they give LnN. Here also it has a plus 3 oxidation state. Here also on heating with sulfur, they are forming the plus 3 oxidation state, which is Ln2S3. Now let us just have a quick revision of lanthanoid that we have studied. Okay, so first of all, the most important part is the electronic configuration. Okay, so you just look at the electronic configuration. So in this you have to remember for cerium and for gadolinium we have the exception. Okay, again for this, that is cerium, we have an exception in there plus 2 oxidation state also, in which the one of the electron from 5 2 goes to 4f. Next, if you talk about their atomic radii, it is decreasing gradually, and their ionic radii is also decreasing gradually. So this is your plot here for plus 3 oxidation state, but for plus 4 it was difficult to say calculate the atomic radius or ionic radius, so it is not mentioned. For some metals it was possible, like cerium, and for Pr and for Tb. In the plus 4 oxidation state, we have calculated their ionic radii. Similarly for Sm, Eu, Tm and Yb in their plus 2 oxidation state, we have calculated their ionic radii. Now talking about their appearance, they all have a silvery white appearance, and their melting point lies between 1000 to 1200 Kelvin, and the exception is samarium, which is having 1623 Kelvin. Now talking about their adsorption band, so they are colored in nature except lanthanium and lutetium in the plus 3 oxidation state. If we talk about the magnetic properties, then lanthanium 3 plus, cerium 4 plus, ytterbium 2 plus, and lutetium 3 plus, they all have diamagnetic behavior because there are no unpaired electron present. Okay. Now, if we talk about the first ionization enthalpy, then it is 600 kilojoule per mole, which is good in accordance with calcium. So the starting members act like calcium, whereas the end members, they act like what? They act like aluminium. So if we're talking about the reactivity. Now the plus 3 oxidation state are having a smaller delta H value because of the because they are forming a stable oxidation state, and in addition to that, the lanthanum and gadolinium and lutetium, they show a very lower value of third ionization enthalpy. Why is it so? Because they are going to the full-filled or half-filled state. Okay. So this is a thing I have told you. After at last we have this diagram, which is very important. So each of this is very important. These reactions are very important. So in each of these reactions, you will notice that they are again moving to their stable oxidation state, which is plus 3. Okay, in each of these. So if you talk about Ln2O3, so 3 2 is 6, 2 3 is 6. Okay, so oxygen is in minus 2 oxidation state. So 3 into 2, that is minus 6. Now this compound is to be neutral. So 2 into plus 3, that is plus 6. So plus 6 and minus 6, it's 0. Here also sulfur has a plus 2 oxidation state. So plus 2 into 3, minus 2 oxidation state. So minus 2 into 3, minus 6. So similarly, lanthanum will have plus 3. So 2 into plus 3. Here also nitrogen is having oxidation state of plus minus 3. So therefore lanthanum will have a plus 3 oxidation state. Here also OH minus has an oxidation state of minus 1 because the charge on it is minus 1. And there are 3 such OH minus. So 3 minus. So lanthanum will also have plus 3 oxidation state. If you talk about the halogen, they again see we have X. So X is what? Halogen, fluorine, chlorine, bromine, iodine, which will have oxidation state of minus 1. So there are the 3 such halogens. So 3 into minus 1, minus 3, and lanthanum will have plus 3. Similar for acid. So if you react it with acid, then they will release H2. And similar is the case for what? Hydrogen. So if you react it with hydrogen, they will form LNH3. Okay, clear? So this was for today's lecture. With this, I end my lecture. Thank you.